This is my lab report on Lab 4 Oscillations of Physics 2211. So for a brief introduction, the purpose of this lab is to analyze the motion of an oscillating spring mass system from a video and determine if the model follows the energy principle by using a simulation that was constructed through coding on GlowScript. The physics that we're using for this would be Newton's second law, which is the change in momentum, the energy principle, and also other spring force equations and gravitational equations to form our work and our Fnet. So Newton's second law we worked with before, Fnet equals all your total forces in the system, which in this case would be the force of the spring and the force of gravity. And then your energy principle is energy of the system is equal to the work done by the surroundings plus your Q. After tracking the mass in Tracker, we're able to get these points as our observations of how the mass had moved on the X and Y axis as shown. And the initial position is what was shown and the initial velocity is what was shown. This is important because this is what we'll use for our model to see if our data coincides. This is the code that we used for our simulation. In the first block, that's quite small, you can see all the initial conditions. And then in the second block, you can see all the spring forces and the vectors that go in to calculate those spring forces and the kinetic energy. And then the last block is a continuation of these calculations and everything else that's needed to conclude the simulation. Notice that it includes the force of gravity as well as the force of the spring and then adds them together to find our Fnet. That's because those are both the forces that were included in this system, not accounting for air resistance and anything else that was worldly. So shown here are our observations on top of our model. Blue is our model and red is our observations. And one thing that you can notice is that the periods of the oscillations do line up very well, which means our model is fairly accurate at that. However, the amplitudes are very different. The amplitudes for the model are much larger than the ones for the experiment. We think that is due to just real-world forces that would cause inaccuracies in determining the true net force, and also inaccuracies when calibrating the distance because there was no set distance in the video used, so we had to use our best approximation based on what was given to us to create a good distance as to create a good rule of measure for measuring how far the object or the mass had moved on the spring. Now, to answer the other questions for this lab, it was found that the energy principle was satisfied. That's because our delta E remains 0 for the duration of the entire observed motion. There was no change in energy, which means that energy was conserved inside the system based on the way we calculated. And even though there are different types of energy, as I said, they all sum to 0 just because it's different transfers of energy. You know, energy gets transferred from kinetic to potential, gravitational potential, and back and forth. We also found that the period of oscillation in motion was 1.75 seconds in the x direction and 1.5 seconds in the y direction. This was pretty accurate from our model and also our real data as shown. The periods lined up really well. So our model was fairly accurate and we were able to predict the motion fairly well. The only thing we weren't able to predict was the exact distances as seen in the real experiment. And again, that's likely due to just measuring error because it is Tracker and there's no set scale, or just outside forces, like small accounts for outside forces that add up, such as air resistance and other things in the room.